So this is the NanoVNA that we are talking about. Let us turn it on and do a one-port calibration. Turns it on. Looks like it has set the frequency automatically, which should be the full range, but since I've changed it previously, it is showing 150 megahertz center. We'll start it from 50 kilohertz to 200 megahertz. Yeah, that's fine. 200 megahertz. Now we need to do the calibration. Calibrate. We can reset and see how it works. Yeah, reset automatically changes the calibration to default, which is no calibration at all. Let's do the need to connect the open first. This is the SMA open. That's how it looks. Connect it here. First of all, we need to remember that this port is not where we are going to connect our antenna. We will be connecting our antenna to the cable. This is the cable. We'll be connecting the cable, and we will be calibrating this VNA to take the reference as the end of the cable, the other end of the cable. This is the other end of the cable. This is where we will be calibrating our VNA. Now we connect the SMA open. Okay, we are done. Now press it. Now I guess we need to reset it. We need to press the open. I don't know. Yeah, now we connect the short. Remove it gently. Connect the short. Okay. Now we connect the load. Need to check that the short looks like this. It is connected. The center pin is connected to the body. This is the short. Now we connect the load. Load looks something like this. You may have some different calibration kit. And there we are. We can immediately see the S11 trace has fallen down to minus 50 dB, which is a good sign. Now we are basically done with the one port calibration. Don't have to do all these things, but because it doesn't take into the consideration, you can simply press done, and I will save it as 1. Okay, we are done calibration. Now this is a open-ended cable. Okay, if you know the basics of Smith chart, you can see that the right side of the Smith chart is open circuit, whereas the left side, which is this side of the Smith chart, is a short circuit. Now if your right now or marker is at the right side, which is exactly the reason, because it is an open circuit right now. If you connect the load, the SWR becomes 1. So if you connect the load, if SWR becomes 1, the marker should come in the middle, exactly in the center. Oh, has it come in the middle? Yes, it has, which is indicative of a very good quality load. It may not be very good quality for high frequencies, but for the frequency range that we are looking at, doesn't really matter. It's a good load in my opinion. And there we are back at the right side, an open circuit. And that's how we calibrate this VNA for one port measurements. You can always do the two port measurement where you have to uh, do a through calibration as well, where you have to connect the this port to this port, so you can measure the antenna response, or not antenna response, or filter response, or coaxial cable, how good the cable is, how much attenuation the cable is giving, and all those sort of things. So we'll end our video about calibration here. Okay guys, so we saw the calibration procedure on the screen of the NanoVNA, but how do you do it on a PC? Doing it on a PC is very easy because you have a much bigger screen, a very good software. You don't have to fiddle on the screen with your fingers. So that is one of the advantage that I like over the touch screen, because the touch screen is quite small, and you know, if you have fat fingers, it's going to be a problem touching the buttons here and there. So I've connected the NanoVNA over USB. Let me turn it on, and we'll see it appear on this COM port list. Here I've turned it on, and now you can see USB serial device on COM3. I've downloaded the NanoVNA software from somewhere. I'll put the link in the blog post. I'm going to open that software and let us see how it works. This is where I have the NanoVNA. I'm going to open this now. Here we have the NanoVNA. I'm not doing any screen recording. I'm recording this off my phone. Anyway, as you can see, we can see the COM1 and the COM3. We are going to select the COM3 because that's what we saw in the device manager. COM3, connect. Now we have only connected it, but we need to tell this software to keep capturing the data. Okay, we press this. We are not getting anything here. I guess we need to disconnect and reconnect. Let's try it again. No data again. Okay, let's try restarting the device. Okay, restart the device now. Disconnect, connect again, get data. Okay, now we have it. Okay, we'll set this plus 10. We have the full range, 10 dB to minus 70 dB. Okay, now this is only one capture from 100 megahertz to 200 megahertz because that is what the state I had stored previously. Now we need to press this auto refresh button here, which will make this capture the data continuously. Now we have lost the calibration. We need to recall the calibration that we had done previously. We'll do recall 1 because that's where we stored it. Okay, 50 kilohertz to 200 megahertz. That is the one that we saw previously. As you can see, there is a little error here. There's some error over there. Calibration error, as you can see. So what we will do is we'll recalibrate this, and this time we are going to do it over the PC. So let's start the calibration process. Oh, and by the way, I've selected the S11 and the S21 in the rectangular plot. I have not selected this mid chart. I've used the rectangular plot here. So I'll press auto, which will give us the S21 response, which is way too low. And we'll keep this as auto as well. Okay, so let's start the calibration. We'll press this calibration. I'll connect the open. Connecting the female to female adapter. Need to observe carefully that I held the female adapter statically, and I only rotated the SMA nut. That is how you should use your connectors. Otherwise, you're going to cause wear and tear. Your connectors are going to get useless over time. Now we have our SMA open. Connect this here. Okay, press open. Okay, disconnect this, then connect the short. There we have our short. Press the short. Now you can observe that when you press any of these buttons, it becomes an underlined button, which is good. I mean, if it's underlined, you should know that it's already been done. Now we go to the load. There we have it. The load has caused the S11 to drop to 50 dB as we saw on the screen previously, which is a good sign. Okay, I like this now. Where's the load? And we are done. We can do the isolation thing, it's not really required. And there's no through either, but just for the sake of it, I'm going to connect the second port of the VNA. I'm connecting this port to this port through the cable. Now naturally both the ports are matched to 50 ohms. If you observe the schematic, there are multiple 3 dB attenuators, 6 dB attenuators in the circuit, which result in a very good match. and good match equals good SWR or reflection coefficient, which is S11. You are getting a 55 to 60 dB of S11 in our measurement range, which is a very good thing. As the leakages increase, the S11 starts degrading at higher frequencies. If you go to 900 megahertz, this S11 is going to be somewhere in the 50s or 45-40 range. So that's natural. You have to build very good circuits, good mechanical assemblies. You have to take into consideration the electromagnetic radiation, leakages, and all sort of things at those frequencies. So we are dealing with low frequencies here, so we are not going to talk about all those things here. Connect the, press the through button now, and we are done. And I'll save it as 1 again. Okay. Now the screen shows actual measurement graph, which is good considering that S21 is almost 0 because we have calibrated the cable out. We'll check. Now we are going to do S21 measurement of a directional coupler that I tried to build some time ago. I'm injecting the stimulus signal into this port, which is going here all the way to here. It's getting reflected back, and we should see some coupling here. And as the frequency increases the coupling factor should increase. So for example, if it's minus 40 dB at 10 megahertz, you should see maybe minus 30, minus 20 dB coupling at higher frequency, for example 100 megahertz or 200 megahertz. Since this is a low frequency directional coupler, it's quite large, and this is let us see how this performs. It's a very basic test. I don't even know the proper characters. I don't remember the characteristics of this thing because I've designed it some time ago. It's been more than a year. So let us go through this thing, how it performs. Let's go back to the PC. By the way, you can see I'm injecting the stimulus on this port. Signals getting reflected from this open port, and we are measuring this at the coupled port here, which is going inside this. Let's go back to the PC. Directional couplers allow us to measure forward and reflected power without loading the main line. And if you have a power amplifier and you want to measure how much power it is pumping out, you will have to use a directional coupler because it does not load your directional coupler at all. It takes a very small percentage of the power that's going out or coming back, and you can see that on the coupled port. That is exactly what we are seeing here. Now the orange line is the S11, which is very near to 0. 0 means that entire power is getting reflected back. There's no coupling. There's no delivery of power at the output. All the power that we are pumping is getting reflected back to the source, and we are measuring this through S21, the coupled line. As you can see, at 180 megahertz, we have something like minus 17 dB coupling. At 80 megahertz, it's minus 23, around minus 20 to 24. So as you can see, that is the problem with these strip line couplers, microstrip directional couplers, is that they operate for a very limited range of frequencies. The coupling is not flat. The coupling is varying throughout the frequency band. So I have this QFH antenna here. I don't know, maybe it should be tuned to 137 megahertz or 130 megahertz, something like that. But we will test this on the NanoVNA and find out. So we should keep this somewhere here. Okay. I know it's a messy room here. So here we go. And here we have the Smith chart and the rectangular S11 plot to put the marker there. Moving the marker. Okay, by the way, looking at the Smith chart, you're seeing a lot of going round and round around the Smith chart. We should be interested at the point which is closer to 1. Wherever the blue line meets or comes near 1, that is the point where our antenna is tuned, and that is the frequency where we will see a dip in the S11 plot, the rectangular plot. So we'll move the marker and we will find out. By the way, the advantage of the Smith chart is that we can find out whether the response at the desired frequency is capacitive or inductive. So in case for circuit or the antenna is capacitive at certain frequency and it's far away from the center, we can add some inductance to it to bring it down to the center. That's how we match impedances if they are not tuned. That's how antenna tuning works. That's what the antenna tuners do, automatic tuners or the manual tuners. That's what they have. They try to bring the impedance to the center so that it becomes completely resistive, so it starts to resonate. Anyway, I'm not able to explain it very clearly because that's not what we're talking about, so it's just coming off my mind. I'm trying to explain those things, but just ignore them because I haven't gone into details for them. Now we can see that the antenna is tuned to 133 megahertz exactly. That's surprising. And you can also see on the Smith chart the marker is very near to 1, which is a good indication. At 133 megahertz it is minus 29 dB or minus 30 dB, you should say. It's very good response. That since it's sticking to the wall, the response might be slightly poor. So let me try to move the antenna and we'll see how the response changes. So as you saw, the antenna response went all the way to 138 megahertz, and the antenna was designed for 137 megahertz, which is very close to what we designed for. What the fabrication and the design are kind of matching very closely. Now when you test an antenna, all you care is whether the frequency of your interest lies within the minus 10 dB bandwidth on the S11 plot. If suppose you tune the antenna design an antenna for 140 megahertz or 137 megahertz in this case, it is not necessary that the downward trough or the S11 notch lies at 137 megahertz. It may lie at 134 or maybe somewhere around that. 137 megahertz is just an example. It could lie in 138 megahertz or 136 megahertz, but it does not mean that it won't work for 137 megahertz. If 137 megahertz, if the S11 at 137 megahertz is below minus 10 dB, for example, is the minimum required number for good performance. So if it lies below minus 10 dB S11, it is going to work. So that's any frequency between 2 minus 10 dB points is going to operate. The antenna is going to work. Let us find the minus 2 10 dB points here. So right now we'll move the marker. Okay, so there we have 136 megahertz. And my 125 megahertz. So our antenna is going to work between these 2 points, 125 megahertz to 136 megahertz. And that's just an example that we saw how this thing could be used for analyzing RF antennas or circuits, and it seems to be working excellent. So with this we'll end our video here.